Last time, actually, any questions before I begin? We were talking about diffusion bonding last time. And diffusion bonding, actually someone came and asked me right afterwards, I forgot to say this, it produces nearly perfect joints when everything's going well. You have the right material and the right temperatures and everything else. But it is very limited. It can't do all materials. And when I say it can't do all materials, some are very difficult to bond, like aluminum and magnesium because of the surface oxide. But other materials, there are iron-based materials or nickel-based materials or copper-based materials that even if you could bond them, you're going to lose the mechanical properties that you put into them by doing heat treatments ahead of time, because this whole thing has to occur at something between 6/10 and 8/10 of the absolute melting temperature. And cost is a big issue here because you're talking tens of hours for the heat treatment, and you're talking expensive fixturing to get something on the order of 5,000 psi contact pressures. You're talking about very precise machining, and if you have curved surfaces, the two curved surfaces have to have the exact same curvature, okay, or they don't match, right? They got to be very close together. Or flat surfaces have to be very flat. So preparation of the specimen so that the contact surfaces mate very precisely, fixturing, and the length of heat treatment all drive the cost. And that means you're typically talking aerospace type of applications. Not always, but usually aerospace. And certainly not talking things like automotive applications where you can use a lot cheaper. You must use much cheaper processing. Diffusion bonding uses heat to dissolve, diffuse, or evaporate away the contamination. It evaporates away the moisture in the oils, and it diffuses and dissolves the oxides or sulfides or whatever else is on that surface, carbon sometimes. And it uses heat to form the asperity. So going back to this theme of you got two problems to bonding things together: surface contact area and contamination. And the way diffusion bonding solves it is just adding heat and pressure. I guess I could say heat and pressure here. What do I do with my piece of chalk? Okay. To do that, okay? We're going to talk about in a little bit transient liquid phase diffusion bonding, which overcomes some of those things. But first, I also mentioned diffusion bonding many times being a solid state process. It's useful to join dissimilar materials. And one of the problems with dissimilar materials is that this is a slide from a presentation some students' research once. But basically, if I look at joining two dissimilar materials and I look at thin sheets of material, so my big buildup of stresses is only in one dimension, or if I look at something axisymmetric, where my stress pattern across that interface is going to be in both dimensions, it turns out that the strain energy, in this case, in the plane strain stress case, goes as 1/2 kx squared, where x is the dimension, the long dimension, but the bond strength only goes by the strength of the bond, F times that dimension. Actually, it's F times x times 1, but if we're just talking unit dimension thickness. So the strength goes as x, but the strain energy that you're building up goes as x squared. And if you looked at it axisymmetrically, you'd find the strain energy goes as r cubed, and the bond energy goes as the area, which is r squared. And it doesn't matter whether you're two-dimensional or three-dimensional, the strain energy builds up at one length dimension higher than the strength of the joint. And the strain energy is what causes the thermal expansion problems. And what that means in a practical sense is the bigger the bonded area, the worse the thermal expansion mismatch gets. And it's going to be proportional to the length dimension, okay, if you're thinking in terms of dimensional analysis. And as a result, when we're talking about, doesn't matter whether we're talking about diffusion bonding or whether we're talking about soldering silicon wafers to their substrates. I told you the silicon chips usually don't get much bigger than about 1 centimeter on a side. It turns out people like to bond ceramics for cutting tools to a steel support to get very high machining speeds. One of the kind of great successes in manufacturing over the last 20 to 25 years, and a lot of this was Air Force money, to improve the rate at which we can remove metal from big forgings or things like that. Okay, it turns out that the spindle speeds of the cutting tools on a milling machine or a lathe and everything have gone up by more than an order of magnitude, in many cases 2 orders of magnitude, and sometimes approaching 3 orders of magnitude in the last 25 years. And so it turns out a lot of the machine tools that we had from 25 years ago are junk because they can't spin fast enough to match the cutting tool materials. And a lot of this is just improvements in cutting tool materials. When I was a student, we used to sharpen hardened steel pieces. We could go to a grinder and we could shape our cutting tool and we could go use it on the lathe. My wife used to get upset because I'd throw the cutting tools in my pocket. And I'd always cut up my pockets would always have holes in them because of the sharp cutting tools I was throwing in my pocket. But in any case, nowadays you have a little ceramic insert or a carbide insert. And a lot of times people want to braze those, not necessarily diffusion bond, but braze those, and typically that's fine as long as they're only about 1 centimeter in length. It's very hard to braze a ceramic to a metal when you get to more than about 1 centimeter because the residual stresses build up and the whole thing destroys itself from the residual stresses from the thermal expansion problems. You have the same thing in diffusion bonding, have the same thing in soldering and ceramics. And it turns out you only need about 300 degrees Fahrenheit, or actually, let's call it 200 degrees. If I know that the strain is equal to the thermal expansion times delta T, it turns out the thermal expansion difference between a metal and a ceramic is something on the order of 10 to the minus 5 per degree C. Well, if I have 10 to the minus 5 per degree C and I multiply by 200 degrees C as a delta T, I end up with a strain of 0.002. What do you know about a strain of 0.002 or 0.2%? That's the yield strength of the material, right? And remember the stress strain curves? Stress strain curve, you kind of take the slope at 0.2% strain. That's usually where you kind of define the yield strength of the material. So if I get that much strain, and it only takes 200 degrees centigrade, so I can get some pretty high stresses. And then, of course, the stress you get is proportional to the elastic modulus. If I'm talking steel, and I have this is my thermal expansion mismatch difference between the steel and some ceramic, and I heat the steel, there's a processing, I process at 200 degrees centigrade and then cool it down after I've made the joint. The modulus of steel is 30 million, and that means the residual stress in that joint is going to be 30,000 psi with only a 200 degree temperature difference. Okay? Or you can think, we were talking before about flame heating steel to bend it, and actually it's one of the things in my World Trade Center paper. I think we handed it out in the packet of stuff. I don't know. Basically, you heat up steel a temperature differential of 200 degrees C, and you'll reach something close to yield level residual stresses in steel, or 30,000 psi stresses. That may not be yield level in HY80, but it's yield level in the carbon and the typical mild steels that we use for construction and stuff. So it doesn't take much of a temperature difference to create some big stresses on these things. And there's something else I was going to say, but that's okay. Now, how does diffusion bonding occur? Well, this is a nice little cartoon. You've got copies of it in your handouts. It comes out of the welding handbook, as far as that goes. Basically, if I have, this is supposed to be showing you the asperity contact between two metals that are coming in contact. They're trying to give you a dimension here, so that's 100 nanometers. It's not very large dimension. So you're talking a very finely polished surface, but on a microscopic, on an atomic scale, it's very rough. Well, what happens is you squeeze those together, you'll have contact at the asperities, and this is called stage 1 for stage 1 diffusion bonding. And the next one is cleverly stage 2. And then we have stage 3. So the first one's asperity contact. The second one is basically where the diffusion starts to take place, and I still have separate grains on either side, but this heavier black line is basically showing you where the bond line is, and then you have pores in here. So you have the bond line separates grains in the metal, and you have porosity. So you've got a perforated grain boundary as your interface, and that's not a full bond. And then in stage 3, I'm sorry, this is stage, I've got different. We'll call it stage 0, stage 1, stage 2, and stage 3. I guess they got it written here. The next one is grain growth across the interface. And the last one is they call volume diffusion. And it turns out it's useful to think about this in this way because several things happen. Here's your initial asperity contact. Here you started to diffuse and you now have a perforated grain boundary with separate grains on either side. Here you're starting to get grain growth and you're starting to trap some of the porosity inside a grain. That's a problem. If you know anything about diffusion, bulk diffusion to get rid of porosity takes forever. Now if I have the porosity still contained at a grain boundary, then the pores, the vacancies in the crystal can annihilate themselves just by rearrangement of the grain boundary, and you only have to move a couple of lattice distances to eliminate porosity. Okay? But if I have volume diffusion, I've got to move those atoms all the way from the inside of that grain boundary, all the way out inside of that grain, all the way to the surface of the grain, in order for the grain boundary to rearrange and annihilate the vacancy. I can't get rid of a vacancy on a crystal lattice. I can move it around, but I can't eliminate it. Okay? There's nowhere for it to go. It has to get to the edge before it can be eliminated. If you just were to play with a bunch of pennies on a table and you had a vacancy in there, unless you change the outside circumference of those pennies, you'll never get rid of that vacancy of a penny. You have to let the vacancy diffuse to the surface before the whole thing kind of collapses in a little bit, geometrically. And that basically is the same thing that happens here. Eventually, if you get no more grain boundaries and you only have volume diffusion, your whole process is over. So it turns out it's also interesting that at this point, pressure is important. But for these two, you no longer need pressure. The thing is, you've already bonded it together. It just doesn't have a very strong bond. It's got a perforated grain boundary in one case, and it's got porosity within the grains, which is aligned in some sort of plane. But after this, I mean, it's really only in the first few hours of a diffusion bond. You may have tens of hours for the diffusion bonding cycle, but it's only the first few hours you need to apply the pressure. And so there are cases where people will essentially do stage 1 in a furnace, and then they'll take it out and use the fixturing again if you need a higher volume production. You only need to do stage 1 for the first few hours, take it out, and then you can just put the parts in another furnace without any fixturing, and they'll hold together, and you'll get stage 2 and stage 3 without applying pressure. Okay. But all of this also places limits on the temperature. I told you that the bonding temperature should be somewhere between 6/10 of the melting temperature of the material and 8/10 of the melting temperature of the material. And it turns out the 6/10 is because if I don't get enough temperature to soften the material, I'm not going to be able to deform those asperities. Instead of using 5,000 psi, I can do a diffusion bond at 5/10 of the melting temperature, but I might need 10 or 20,000 psi as a fixturing pressure, and now the costs go, you know, through the roof, right? But if I'm talking about, so on this end, I'm limited by pressure, and time. The rate of diffusion is an exponential, goes exponentially with time, and so my time, not only does my pressure go shooting up, but my times go shooting up, and it may be hundreds of hours rather than tens of hours. And so I have to get enough heat in, and typically that's somewhere around 6/10 of the absolute melting point to not be limited in terms of the cost of processing in terms of pressure and time. Here, above this, I've got a problem of grain growth. Once I get to stage 3, the process is over for all intents and purposes. To get rid of that porosity, it'll take you 10 years for a heat treatment in stage 3, because you're talking about diffusion over hundreds, if not thousands, of lattice spaces as opposed to 2 or 3 lattice spaces. And the diffusion time goes up as the square of the diffusion distance. So if I go up by a factor of 1,000 in distance, I go up by a factor of 1,000,000 in time. Well, I don't want to do it for 1,000,000 hours, okay? I don't even want to do it for 1,000 hours. So once I get to the point where the grain boundaries have left behind and swept past and left behind volume porosity, then the process is over. And it turns out grain growth occurs quicker at higher temperatures. And so I don't want to push too high in temperature, or I'm going to get to stage 2 and stage 3 before I want to. And I'll leave too much porosity at the interface. So it turns out you got a fairly narrow range of processing temperatures, and that limits the process. Okay? So that's diffusion bonding. And I guess the one other thing is, I mentioned superplastic forming last time. What was I thinking of when I was talking about stress strain? I don't remember. I had a story. But anyway, I'll tell you this story. I mentioned superplastic forming and diffusion bonding. We talked about titanium is very easy to diffusion bond because above 900 degrees C, it dissolves away its own oxide. It will dissolve its own oxide. And a little bit of oxygen in titanium is not harmful. In fact, you use oxygen in titanium to give it some extra strength, just like you use carbon in iron to give steel extra strength. Of course, it has the same type of effect. Carbon will make iron somewhat less ductile, a little more brittle, and oxygen in titanium will make the titanium a little less ductile and a little more brittle. But in fact, commercially pure titanium you can buy in typically 3 grades, and it's just 3 different levels of oxygen. And you get like 0.1% oxygen in titanium or actually at the higher levels, I think it's 0.2 to 0.3%, which is similar to the amount of carbon you have in a lot of your steels. Okay, you have about 0.1% carbon in a bridge steel nowadays. In the old days, it might be 0.2 or 0.3. The old titanium used to have 0.2 or 0.3% oxygen. What we call extra low interstitial titanium will be like 1,000 ppm oxygen as opposed to 3,000 ppm. You get to 10,000 ppm oxygen, which is 1% oxygen in titanium. It'll snap like a ceramic, almost. I mean, it's almost as brittle as a ceramic. Very few things are as brittle as ceramics, but anyway, that's another story. Okay, so titanium will dissolve away its oxide, and so it forms nice, clean, contamination-free surfaces when you heat them up for diffusion bonding. And it has another property that you can cycle it through its crystal structure change, and you can get very, very fine grain size. And if you get very, very fine grain size, it turns out, remember this, well, I have a turbine blade here somewhere. Here's a turbine blade, or vein. When they first started working with, after World War II, making jet engines and stuff, they used just regular old cast stainless steel or whatever, and had a bunch of grain boundaries and stuff, and they may only be able to operate at 1,200 degrees Fahrenheit in the engine back then. And they've crept up today, well, by 1970 they had crept up to around 1,800 degrees Fahrenheit. Now, why is that important to go from 1200 to 1800 degrees Fahrenheit in operation of an engine? It improves thermodynamic efficiency and power and everything else. You get greater power density. Nowadays, GE's latest engine is 110,000 pounds of thrust, which you probably only need 2 of those engines to fly a 747 or to take off with a 747. They got power to spare. In fact, they put those on a 777. They've only got 2 engines, and they really only need about 70 or 80,000, but you can get 110,000 out of those engines. So you got power to spare in these engines now. But that's not what's driving it. What's driving it is every 50 degrees Fahrenheit increase in temperature will save the commercial airlines about $3 billion a year in fuel costs because of greater efficiency. It's not the takeoff thrust that's yeah, they like to advertise their takeoff thrust because it's telling you the power of the engine. But, you know, in terms of fuel cost, it's that cruise energy that is important, right? So it turns out every 50 degrees is worth one heck of a lot of money, okay? And so going from 1200, from 1945 to 1970, going from 1200 to 1800 was a pretty big improvement. And that was all done by going from stainless steels to cobalt-based superalloys to nickel-based superalloys, and also by going from polycrystalline grains to directionally solidified grains. I don't have any turbine blades of directionally solidified, but basically you grow it almost like you grow a silicon crystal, and you have all your grains growing in one direction. And because it's the weakness at high temperatures along the grain boundaries, okay? When you're pulling with the stress on it, and you got these grain boundaries, you can create, because of that stress, vacancies. We talked about annihilating vacancies. You can create vacancies if you apply a tensile stress. You'll create vacancies. If you get enough vacancies, you'll start creating voids at the grain boundaries. Just like we're getting rid of them in diffusion bonding, you can create them. And you can perforate this thing, and the thing finally fails by failing along the perforated grain boundaries. You're just creating vacancies by applying a tensile stress. Well, that's what these things do, is you apply tensile stress as it spins around in the engine. So they got to the point where they made all the grain boundaries going perpendicular or parallel with the stress axis, so who cares? You don't have any stress trying to create grain boundaries, and that was good, except the grain boundaries all have a little bit of orientation, and so they create some. But you got a tremendous improvement, probably a couple hundred degrees Fahrenheit, from going from polycrystalline to unidirectional grains. And then in the late 60s, they really didn't commercialize it until the mid-70s or so. They started growing single crystals, no grain boundaries at all. And when I passed around the one that's filleted and shows in, that's all a single crystal. And so you can cast these things polycrystalline and probably sell them for a couple $100 a piece. But when you start growing single crystals, which takes you like 6 or 7 hours to grow that single crystal in $1 million furnace, now you may be able to grow a dozen at a time, okay? But still, it gets pricey, okay? $1 million furnace is going to cost you $1,000 an hour. So just your growing of that single crystal ends up costing you $500 to $1,000 per blade, and you haven't done any of the other processing or paid for the metals in it. Nowadays, we actually put rhenium, up to 5 or 6% rhenium in these things, and rhenium is in the platinum group of metals. It's one of the less expensive of the platinum group, but it still goes for about 60 bucks a pound, okay? So it's starting to get a little pricey on these things. And you can't just simply recycle these alloys like you do everything else, because when you grow them, they get oxide inclusions and things like that, and those are bad. So you basically have to send them back and reprocess them completely. So that's why it drives the cost, but you're talking about saving billions of dollars in energy for doing all this, and you end up making things that cost $4,000 a piece. Well, so you get creep if you have grain boundaries. The metal will deform readily, and it turns out what you do in superplastic forming is you make lots of grain boundaries, and you get it to the point where the creep occurs at very, very low temperatures, so that you can form it by a creep process rather than just mechanical deformation. So it turns out with superplastic forming of titanium, you can actually take a titanium billet, a disc, just a flat pancake sheet piece of metal, And instead of having a whole series of forging dies and going pound, pound, pound as you change the shape with this thing, which is very expensive. You've got millions and millions of dollars worth of dies to make one aerospace component. You can now do what they call isothermal forging. You basically make carbon-based dies, which don't have tremendous strength for impact. But what you're going to do is you're going to put superplastic titanium in there, and you're going to keep it hot, and you're going to have these carbon or carbide dies that can take very high temperatures, and you're just going to slowly squeeze it and superplastically form one set of dies to get your final shape. So you save tremendously on die cost. Yeah, you're not going pound, 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 but actually in terms of total processing, if I had to pound it through 4 sets of dies to get something, and all the, buffer inventories around each one of those sets of dies, if I just take one disc and I put it in the furnace for half an hour and it slowly squeezes it, and with one set of dies, I can recover those costs, because we're talking low volume production. So that's superplastic forming. Well, it turns out the Air Force in the 80s, they were doing isothermal forging in around late 70s, early 80s, and it's quite widely used for titanium alloys now. But then in the mid 80s, they said, well, I can do more complex parts, and I can diffusion bond them at the same time, because titanium diffusion bonds easily. And so you can make very complex structures with clever fixturing by doing superplastic forming and diffusion bonding. Now, so why do I hold this? Because superplasticity was actually discovered by, I think it was someone in Germany in the 1930s. And he published a paper on it, but everyone forgot about it, maybe because of World War II or whatever, but everyone forgot about it. And about 1960, Professor Backoffen, who was here, was studying the effects of grain size on metal forming. And he found that as he got to very fine grain size, he could do tremendous draws. And this actually, what he did is, this happens to be an aluminum zinc alloy, and it goes through a solid state phase transformation too, and so you can get very, very fine grain size. We're talking about typical grain sizes in metals that are processed might be anywhere from 20 to 200 microns in size. We're talking about getting down to 1 to 5 microns, very, very fine grains, to get something that's super plastic. And what Backoffen found is he got finer and finer grains, the ability to stretch, the ductility in a tensile test went up. And typical ductility in a tensile test might be 30%, 40%, 50%. Well, when you get very fine grains, you can get 400%, 800% stretch in a tensile test. And it starts to form like it's a piece of glass. Glass is what we call a Newtonian liquid. And actually, you can just stretch it out. If you've ever seen glass blowers, you can just stretch it out to tremendous lengths before it necks down and breaks. And we don't need to go through all the stuff of that, but Backoffen basically reinvented this stuff. And he was, in the laboratory, he was looking at aluminum zinc alloys, and Boston area, because of Paul Revere and other people, used to be a big area for silversmiths. It's not as big as it used to be, but he went down to some of the companies, the silversmith companies, and this was some sort of little candy dish or something, and ordinarily you'd have 6 or 7 dies to make a silver part for someone's candy dish or whatever it was. And he could basically form it, and he could take the last die, and you just put gas pressure on one side, and you just slowly form it in there. Actually, you can see, didn't form quite as well around the little corners at the end. Probably could if you left it in there long enough. So it turns out the story was he rediscovered superplasticity in the early 60s, and now the Air Force uses it to make aircraft parts and stuff in titanium rather than aluminum zinc. IBM, which is a huge company, still a good-sized company, but it was becoming the largest company in the world. It never did, but it was heading towards, its growth was tremendous in the 60s and 70s. And so they used to make things called typewriters, okay? We don't, okay? You still see some somewhere. My secretary has one. It's good for doing labels. I know what a typewriter is. Okay. So IBM had this office products division, and they had to make little aluminum parts of complex shape. And a lot of these had to be forged, which meant expensive dies. They were small, but they had to make a lot of these. So IBM had a project to take aluminum zinc alloys and try to do superplastic forming of them in the 1960s and early 70s. And it turns out that they could make the parts. The problem was that particular alloy, it was hard to get the grains to grow back large enough that they didn't continue to deform even at room temperature under stress. And in fact, supposedly, the story I've heard is the manager of this group was such a jerk, okay, that everyone who worked for him hated him. And they finally killed the whole project because they could never overcome the creep at room temperature problem. You don't have that with titanium parts. And in fact, some of the other materials, you actually, after you do the superplastic forming, you do another heat treatment to grow the grains. So you get rid of the creep problem at high temperatures. They never could solve the creep problem at room temperature in these aluminum zinc alloys. And so they killed the whole group and dispersed them or fired them or whatever. And the group gave the manager, as a going away present, an ashtray made out of aluminum zinc with a rubber band around it so that it would slowly creep. Okay. Just sticking it to them, right? I always thought that was a great story. Just teach your boss what you really think of him, right? Okay. So that's stories on superplastic forming, diffusion bonding, and whatnot. And you got all these complications for diffusion bonding. There is something that we use a lot more now that solves another one of some of the problems that occur from straight solid state diffusion bonding, and it's called transient liquid phase diffusion bonding. And essentially it starts out as a braze and it ends up as a diffusion bond. And remember, diffusion bonding, I use pressure, I use heat, I dissolve away the oxides and stuff, and I use pressure to get the surface contact. Well, if I could put a liquid in between there, then I don't have to have the precise machining tolerances. I get much faster diffusion because instead of my diffusion just starting at small little asperity contacts, I got 100% contact area of the liquid. I also get my initial diffusion is in the liquid state, which is much faster diffusion, at least 3 orders of magnitude, if not 5 or 6 orders of magnitude. My final diffusion is still solid state, but whatever. I can reduce the processing time, I can reduce the fixturing cost. The pressure goes in transient liquid phase, TLP bonding. So it's a diffusion bonding process. Your fixturing costs or fixturing pressures go from 5,000 psi down to about 5 psi. All you really need is enough pressure to hold the parts together, keep them from slipping against each other. So now your fixturing costs are way down. Your diffusion times go from, let's say, 20 to 100 hours down to about 1 to 5 hours. And your temperatures, well, I'll just say temperature range widens. It's not limited just to this region up here. And in fact, you can do TLP bonding at very low temperatures. In fact, we kind of done a lot of work in my lab on what we call LT TLP, low temperature transient liquid phase. And I'll show you some of that. So it turns out transient liquid phase is a process that Pratt & Whitney patented. This is the paper. And TLP, down here it says trademark. That's what the asterisk means. And I think at the end they'll probably say, I haven't looked at this for a while, but probably says somewhere in here. But anyway, this was a 1973 paper, and they don't reference a patent, but they didn't publish this paper until they actually had a couple of patents issued on this, which is sort of interesting because TLP bonding was practiced by the Etruscans in 600 BC to put little gold beads on copper-based daggers and stuff. That's what I said. I mean, the Etruscans. I mean, the Pratt & Whitney got the patent because the Etruscans didn't file an infringement. Okay. But it turns out there was a big lawsuit about 10 years ago between Pratt & Whitney and Chromalloy. And Pratt & Whitney was trying to put Chromalloy out of business. What happened was It used to be that General Electric, Rolls-Royce, and Pratt & Whitney made all their money off selling new engines. But when peace broke out in the early 1990s, okay, the military quit buying so much new hardware. Plus, the ability to repair the old hardware was getting better and better. And so it turns out the repair business got to be bigger than the new engine business. And spares was always a great business anyway. But the repair business was getting better and better. And the original equipment manufacturers, Pratt & Whitney and General Electric and Rolls-Royce, owned the spares business and the new engine business. But they had always let this $5 or $10 billion business of repairs kind of go to other parties, like Chromalloy happens to be the largest one in the world. They're under $1 billion, but I mean, it's a very diverse industry to do repairs because everybody gets one particular part they know how to repair. Okay, now Chromalloy's got more than one, but I mean, if you're kind of a clever little machinist and you can get your FAA certification, you can start repairing that part, and that $4,000 part you can do a $1,000 repair on. Well, Delta and US Air and Lufthansa and everybody's going to beat a path to your door to buy the $1,000 part rather than a brand new $4,000 part. Okay, now you have to qualify it and it gets kind of expensive and stuff. Anyway. Turns out, I was told by a vice president of Pratt & Whitney that we aren't going to give up that $5 or $10 billion business anymore. We're going to take that back. Well, one of the ways they tried to take it back was trying to sue for patent infringement on patents like this. And it turns out it was a huge case. It cost $30 million for one side just to litigate it. That was litigation costs. Okay, and when it was all done, basically the judge tells Pratt & Whitney, go pound sand, you can't have any money, but he also awards Chromalloy $0 in damages. So Chromalloy paid $30 million to defend themselves, and they got nothing for it other than the ability to continue in business, okay, which is what Pratt was trying to do anyway, is knock them out of business, right? Anyway, it's sort of a nasty industry as far as that goes. A lot of, because it turns out, in order to get the certification for the repair, the easiest way to do it is if General Electric or Pratt & Whitney bless your repair, okay? Well, what's their incentive to bless the repair, okay? They're going to lose spares business, right? So guess what? Quite often they'll say, we don't like this repair. And so you go back and you say, why not? And they say, well, we don't, you know, and they just stonewall you. And eventually, it turns out there are ways you can appeal it, and you can submit your data to the FAA, and the FAA can judge whether your repair is good enough, and they can overrule Pratt & Whitney or General Electric, and you don't have to have their blessing, okay? Now, it turns out some of the engine purchasers, like the Air Force or United or whatever, will actually force the original equipment guys to come up with some repair schemes, and to a certain extent, they want to show that they have a lower maintenance cost on their engines than their competitors. And they've only got 2 competitors each, right? And if you're actually military engines, you only got 1 competitor, right? So in any case, these guys do. I mean, Pratt & Whitney and General Electric do develop repair schemes because there is some economic incentive in order to sell new engines to have some repair schemes, but not too many. You know, it's sort of this, you got this kind of fine line you want to walk. Anyway, it's like I say, it's an interesting business. But in any case, TLP got thrown out of that case early on. Basically, Pratt & Whitney had to admit that their patents were no good. Okay, because it turns out Rohr Industries in 1956 was practicing TLP bonding. And they never patented it, but they were doing it. And General Electric was doing it in 1962. But Pratt & Whitney gave it a fancy name. In fact, General Electric called theirs activated diffusion bonding. Okay? They activated the surface by putting a liquid in between. And they didn't bother to patent it because they knew Rohr had been doing it, and they knew that other people had been doing things like it, and they never thought it was patentable. In this case, you actually had someone who thought something was patentable. They went out and got a patent on it. And the patent office says, oh yeah, that's patentable. Good for them. They got it. So how does TLP work? How much time we got left? I got time to tell you about TLP. Okay, you got the paper. Here's the, you got your materials with the grain boundaries, and they actually put a brazing foil in between. They show a brazing foil, but you can put powders, you can plate the material on there, and the inner layer melts. And then what happens is the inner layer has to have something we call a melting point depressant. And it turns out for nickel-based superalloys, the useful nickel melting point depressant is typically boron. Boron lowers the melting point of nickel by like 400 or 500 degrees. So I can put a nickel boron alloy in between here. And lo and behold, did you know that some of the most widely used nickel-based for turbine blade brazing alloys are nickel boron alloys? And you know, I've always thought that basically these people came upon transient liquid phase diffusion bonding, whether it was Rohr in '56 or General Electric in '62 or Pratt & Whitney in the later '60s, because someone left the part in the brazing furnace too long and diffused away the boron. But basically what happens is I've got this liquid layer which has a high concentration, in this case of boron, and this would be what the nickel boron phase diagram looks like. Whoops. Let's get in a little closer here. So this would be, you can do this in lots of systems, not just nickel boron, but this would be what the nickel boron looks like. High concentration of boron, and I hold it at temperature for a long time, and it's isothermal solidification. Asothermal solidification, I can solidify an alloy by going down the phase diagram by dropping the temperature. We're all familiar with dropping the temperature of something to solidify it. Isothermal solidification just goes across the phase diagram at one constant temperature. So you can solidify it either way. You just got to get to the solid zone. Here's the liquid zone. You got to get to the solid zone, right? So you can either go down or you can go across. So you go down in temperature or you go across in composition. Well, how do I go across in composition? I just hold it at temperature, and boron, being an interstitial alloy or an interstitial element, diffuses much more rapidly than nickel and other things, and the boron will diffuse away. So initially you go from a liquid layer that actually expands over time, and then it starts to contract, and then it starts to decrease in composition, and when you're all done, instead of after 20 or 100 hours, after 1 to 5 hours, you end up with not even a braze joint. Actually, this was the braze joint, or this was the braze joint. But if you just leave it in the furnace not for 20 minutes, but for 5 hours, you end up with a transient liquid phase diffusion bond with all these wonderful benefits. Okay, so to give you an idea of what people use this for, they use it for lots of things now. It's been expanding dramatically. But back in the 70s, actually, when I started lecturing this course in mid-80s, I used to say, well, this is kind of a process that's sort of specialized for nickel-based superalloys and stuff. But this is a turbine blade that happened to develop from service some cracks. They're thermal expansion cracks. This part of the blade up here, the vein, is hot, and this stuff down in the root is cold, and I have a temperature difference across here. And if you cycle this enough times, turn your engine on and off, you'll develop cracks. That's a pretty good, see the crack? Okay, pretty good sized crack. Now this one happens to be too big to repair, but you can repair cracks in these things depending on the alloy. This is a nickel-based alloy. You could repair that thing maybe if it was a 1/4 inch in size, but you can't repair it when it's 5/8 of an inch in size, okay? But you can repair it and put it in service for another 3,000 hours. This happens to be a cobalt alloy, and this one's got a little bitty crack in here. I tried to show it up there myself the other day, but I can see the crack with my eye, but you got to really look for it right in the corner. And it turns out that one's too big in a cobalt-based alloy. I mean, you have to go through the stress analysis and the crack resistance of the alloy and everything else. So it's not always big ones that can be repaired. But you can repair, and this TLP bonding is a large reason why lots of jet engine parts are now repairable that were not repairable 25 years ago. We've learned how to use TLP. And you basically take a little solder paste, or not solder paste, it's a braze paste, and it's just a bunch of metal powders. I mean, they'll take metal powder A and they'll take metal powder B and they'll mix them together, and they'll take some magic binder for the powders, something like Vaseline, okay, some grease, and you have someone sitting there. You go in one of these plants, you got these typically women do this work because women are more meticulous than men. They found that women are better at doing these kind of detail little things. And they'll take their little putty knife, you know, a little spatula, a little micro spatula, and they'll basically paint this stuff and, you know, plug it up with this stuff. And they'll stick it in the furnace, and the grease burns off, and the brazed alloy melts, and, you know, the powders all diffusion bond together. And you're
Under any pressure?
in that case, no. Okay, because typically it's not a lot of operating stress down here. You don't like to have cracks that are going to propagate. Not a lot of operating stress. A lot of thermal stress from the thermal cycling. But during service, there's no real stress down here. All the stress is.
When you're doing the bonding, do you have to do any pressure?
You don't even have to put pressure on these things because they will have a little bit of porosity, and you can probably only repair them once or twice or 3 or 5 times. They, you know, depends on. But they will have those. Huh? And they will mark on these things. They're serialized, and you'll know exactly how many times the thing's been repaired. Okay? And for different things, it gets very specific, and someone's worked out all the details of the metallurgy of how many times you can repair it. But, you know, nowadays, for land-based turbines are running 40,000 hours between overhauls. When I worked at the Naval Air Rework Facility in Norfolk, Virginia in 1969, we were getting engines back after 600 hours of service. And we were kind of getting them back to Vietnam and stuff, okay? But that was the overhaul time for a jet engine in 1968. Today, a military engine could be 3,000 hours, it could be 10,000 hours between overhauls. And I can remember what we saw in those engines after 600 hours. And when I think 3,000 hours or 10,000 hours, I think, you know, I'd hate to see, but, you know, they've improved them. And it turns out land-based turbines which don't thermally cycle, I mean, you know, if you got Boston Edison's running a turbine, and they don't, you know, shut it off 3 times a day. You know, they shut it off 3 times a year, right? So you don't have the big thermal cycling stresses, which are actually what kill you on some of the life. And they can run easily from, I just had a student finish up a thesis looking at rejuvenating blades and these were big blades, but they had 37,000 hours on them. And they could have repaired them and put them back into service, but because, well, it's a long story about patents in General Electric in that case. General Electric applied for a patent on an alloy back in the 1970s, and they just kept the patent alive, but they never got granted. And in 1998 or 99, the patent office finally, like 25 years later, decides to issue this patent. In the meantime, it was a great alloy, and a lot of people liked it, and so they started putting it into their designs. And guess what? Now people have designed whole turbine systems. These are mostly land-based systems. It's called GTD 111 is the alloy. And General Electric all of a sudden has a 17-year monopoly on something that's been in these designs for 20 years. So everybody in the world is trying to figure out how to make these General Electric parts last longer, okay? Because General Electric, surprisingly, has raised their prices. Okay. So anyway, there's little things like that. So it's a big business nowadays to figure out how to repair these things. Anyway, I was going to tell you that the student, I can't remember what I was going to tell you exactly how the student was, but the student was, he was looking at 37,000 hours, and I was told that some of these land-based turbines now go for 60,000 hours between overhauls. 60,000 hours, I mean, we're talking 8 years of continuous operation, okay? That's a long time. So, okay, talk to you later.